5 case studies on which, as a team, the class can work. 5 different aircrafts, starting from a simple trainer, advanced trainer, passenger aircraft, military transport, and advanced replacement for, let's say, Sukhoi MK-10 and all that. So that's what we are going to share in the end. So as you have seen from the performance and stability classes, a lot of thing depends on thrust to weight ratio and wing loading, all the performance requirements. So, and since these two are kind of independent of each other, the choices you make are going to be wide impact. So one way to ensure that whatever choice you make of thrust to weight ratio or wing loading ensures that the final design, whatever you pick, does satisfy all the performance criteria. So that's the idea of doing that. And just as a quick recap, these two, wing loading and thrust to weight ratio, dictate what the stall speed will be. If the stall speed is given, then only one value of WS satisfied it. And it's independent of T by W. It also, maximum speed depends on thrust to weight ratio, rate of climb, takeoff run, sailing, turn performance, both sustained and attained turn rate. All of them depend to a large extent on thrust to weight ratio and wing loading. So how do we come to a reasonable choice of a combination of W by S and T by W is what we are going to talk today. The first step, as I said in the last class, was to get an estimate of the W. So once you have an estimate of the W, you can, by this constraint analysis, choose a W by S and T by W, which would then give you a first estimate of the wing area S and also the thrust required. It may happen that the thrust or power, whatever you have chosen, that particular value of engines may not be available. So we'll have to go back and relook at all your performance parameters and look at the nearest engine. So initially, what people have done is design with what's called a rubber engine. Rubber engine means that it give you the thrust or power, whatever you're requiring. And then let's see how that performs. Or the other more sensible thing to do is to get an estimate of the thrust and then look which is the nearest engine which gives you the thrust more than what you have required. Or even if it's slightly less, we can make compromises in some other thing. So that's the way it goes. So I have already covered part of this in the modern combat analysis elective, and also probably in the initial stages of my introduction. But to recap, the basic analytical tool, which relates excess power to total change in energy. That's what we are looking at now. So from the total energy, which is both potential energy and the kinetic energy, any change in each one of them results in a performance. For example, if you increase the kinetic energy and along with that you increase the potential energy, then the aircraft is climbing. Without increasing the thrust, if you try to increase the kinetic energy, but then you are trading off with the potential energy, in which case the aircraft is in a glide mode, gliding downwards. So basically, we are looking at overall energy management, and most of the combat aircraft people talk about energy height, which is just the at that altitude, the aircraft has a certain potential energy and a certain kinetic energy. So that is the one which is used in most comparisons. And this is basically used to highlight constraints on each one of them. And what you see in this figure, we'll first talk about this figure and then we'll go and see how this can be derived. So in this case, in x-axis, you have the wing loading, WS, Newton per meter square. And on the left axis, the y-axis, you have thrust to loading. This is, of course, non-dimensional in a sense. Newton by Newton, it's non-dimensional. So the very first thing you notice is the vertical line here. And this is the line coming from stall requirement. So which means that any wing loading larger than this value here, you cannot meet the landing requirement or the stall requirement. So entire part, the right hand side part of this vertical line is not feasible for T by W and W by S. It is vertical line because stall speed does not depend on the thrust loading. However, takeoff or distance depends very much on the thrust to weight loading and also the wing loading, which says that if the wing loading is small, like on this part of the curve, then because the every square meter of the wing is only taking less number of newtons, with the small amount of thrust you can take off. So T by W load is pretty low at this point where the wing loading is low, especially for takeoff. And as the wing loading increases, the T by W also starts increasing. So you have this line which says takeoff. And below that you have the hashes, which means anything below this line in the same direction as the hashes, that combination of T by W and W base is not acceptable. So similarly, you have one for climb, and this is a quadratic curve which increases very steeply with wing loading, and this is the climb curve. So, and there is also another curve which is for turning. So turning, of course, the thrust loading is reduces if you have a larger and larger wing loading possibility. So this is also a quadratic kind of curve, but reducing in this direction. So if you plot all these lines, you will see that there is a small zone here, a combination of T by W and W by S, which is feasible, which if you pick any point in this dotted or hash zone, what is called feasible design area, then you are assured of meeting all the performance requirement. So the reason we look at this is when you get the requirements, as you will see in the case study, the requirements could be saying that it should have this minimum turning rate, it should have this minimum climb rate, it should be able to take off and land at this distance, and it should have climb rate more than this, and those kind of things. So all that you can put them in terms of this kind of constraint diagram and then choose that. In this case, I have indicated 2 points here. One, this point as optimum design points. From the viewpoint of economy, in the sense that in the minimum fuel consumption, then what you're looking at is basically you're looking at the smallest available T by W in this feasible design. That is this one. But it's possible that that possible T by W, while satisfying the curves, the performance requirements you have included in the constraint diagram, may not be suitable for some other reason, or it may happen that particular thrust engine is not available. You have only higher rated engine, in which case you may have to choose some other point. So there are 2 points here which are optimum design points. Anything else you will have more thrust to weight ratio and not optimal. These 2 are the optimal points. So now let's look at how do we derive this. Okay, so as I said earlier, it's all boils down to energy analysis. A total energy of any object, whether it's an aircraft or a rocket or even a cricket ball, there are 2 possible crucial components of the energy. Potential energy, which you can write it as mg into h. That depends on the height from the some datum point, and the kinetic energy, which is half mv squared. So excess power PS, there is an R term here which you can ignore, that represents other miscellaneous things, but excess power is how much thrust you have over and above the drag, which your aircraft is bound to happen at that velocity. Okay, so if you look at T minus D, or could be because some other miscellaneous drag elements which may or may not be there all the time. For example, missiles and are fired, or drop tanks are discarded, so they can't be added to drag all the time because they are replaceable. So anyway, it's just a component of drag. So T minus D is the excess amount of newtons you have with respect to that velocity. So T minus D by W is a specific excess power. So that into velocity is essentially the time differential of the total energy. Total energy is of course d by dt of h plus v squared by 2g newton. This is a specific total energy. Okay, so now this is the first simple equation you have. And as I mentioned earlier, all engine manufacturers give the thrust rated at sea level, which is a constant, and then they also give you a factor called alpha, which changes with altitude. So it's usually called the lapse rate, how the thrust reduces with increasing altitude. So we replace T by alpha into TSL. The reason is alpha is a known constant, TS is constant, so we can use this instead of variable T. So all you need to do is, given the altitude, find alpha, and then you have the thrust. And similarly, weight of the aircraft also keeps changing with the fuel consumption and everything else. So weight also is expressed as W is equal to beta times takeoff weight. Takeoff weight is fixed. Beta is what you can specify, saying that 50% fuel or 100% fuel or 50% payload and things like that. In which case the weight could be different. It's no longer a thing, but expressing this as alpha times thrust at sea level and beta times takeoff weight removes a couple of unknowns. Now drag as before is a dynamic pressure half rho v square s in half rho v square into CD into S. Similarly, CL is NW by QS. N is the load factor, whether it's doing a 1G maneuver or a 2G maneuver or whatever. So CL is N times W by S by Q dynamic pressure. Now W we have said that we can replace by beta times WT naught. So we have N beta by Q into WT naught by S. So plugging all this into the main equation which we started, we have T sea level thrust by maximum takeoff weight, okay, is equal to beta by alpha into D plus R by beta WT naught plus PS by V. PS by V is the excess power you have. Okay, so this is the equation. Here can be R can be neglected when we are doing that because you really don't know what R could be. That depends on the mission and the different type of aircraft and all that. If it's a passenger aircraft, there is no R. If it is a bomber aircraft, there could be R and things like that. So now what we have to do here, D is there. So D is drag, and that is Q into CD into S. CD itself you can expand it as CD naught plus KCL square, and CL square you can replace that by this term, N beta by Q into WT by S. So this becomes an equation like this. So this is again you are saying that TSL, sea level thrust by takeoff weight, maximum takeoff weight, is equivalent to beta by alpha. Beta is you can specify if it is beta could be 1 or it can't be 0. That means everything else is consumed. Beta could be 1 or somewhere between 0.4 or 0.5, meaning 60% fuel is consumed or whatever. Alpha is the way the thrust changes with altitude. At sea level, alpha is 1. At higher altitudes, you have to find out what the alpha is. Now, having expanded the drag term, you have QS into beta by WT naught, K1 eta beta W square, and K2. The second term is also there, and plus CD naught plus CDR, okay, plus PS by V. So this is the equation which we are going to use now for trying to estimate the T by W. So what we plan to do is we make a table of W by S. As you see here, W by S is there in there's a quadratic term W by S, there is a constant term W by S, and there are other constants which we are not at present looking at. So if I choose a WT by S, then given the altitude, I have the Q, and S is anyway wing area fixed, takeoff weight is fixed, so you can compute whatever is needed for TSL. So let's look at the first case, constant altitude cruise, meaning that altitude is not changing, it's cruising, dV by dt is 0. So when you put this, dH by dt is 0 because it's not changing, dV by dt is 0, constant cruise means lift is equal to W, so N is equal to 1, and values on H. So if you do this, you have sea level thrust by takeoff weight is equal to beta by alpha, K1 terms this, K2 terms this, and CD naught plus CDR by WQ, W2 by dS. So you have on the right hand side one WT naught by S, and then on the one more term 1 over WT naught by S. So you have, it's like constant times factor 5 and another constant times 1 over 5. So here what I do is I form a table of WT by S, and when I form that table, for that WT by S, I compute the TS by T wing naught. So I'll get a table and then I plot it. So that is the figure what you saw here. This figure, I pick a table for wing loading, and I vary from here to here. So I get a term for cruise one line, and then for climb another line, things like that. So this is a constant altitude cruise term. Similarly, you can also get for other conditions. So let's say constant altitude turn. When the aircraft is turning, obviously n is greater than 1. Otherwise, you cannot turn. Lift has to be more than w because the aircraft is banked. So now you have to find out what's the n. Because it's a constant altitude turn, dv by dt is 0, ds by dt is 0, but n is greater than 1. So the n term comes here. So we'll have to plug in that n value and again create a table for this kind of thing. So finally, for other kind of things, you can look at a book by Matt Inglis. It's actually an engine design book, but he has quite a bit of explanation and nicely derived values for different conditions, how T by W varies by W by S. Another term we can look at is the climb, where dv by dt is 0. It's again a constant speed climb, and n is of course nearly equal to 1. It's not equal to 1 because then there will be no climbing, but it's not very far from 1, so n is approximately 1. But h and dh by dt are changing. So in the same equation, you have now 1 over v dh by dt term, and of course, you can analytically derive what is the minimum term for this by differentiating and equating to 0. But you can also plot them with using a graph paper and get the right result. So in this case, for constant speed climb, the w by t minimum w by t, and for that t by w is this depending on q by beta, cd naught plus k, the cd by k. Okay, and there are similar things for turns and everything else you can derive. So, well, let's look at some examples. If the constraint is takeoff ground run, you can use the following equation. Okay, plot T by W versus W by S using this equation. Okay, and for various values of W, you can get T by W. So S, let's say, is given. You are told that this aircraft has to take off in 1000 meters or land within 1000 meters. Then S is known. Take T by W on the left hand side, and for every W by S, you can compute what's the T by W. Okay, so you will get an equation like this: 1.21 times W by S. 1.21 times comes from 11 square. So anyway, I'll talk about that a little later. You know that whenever you have to take off, the speed should be at least 11%, 1.1 times the stall speed, and then when that square that, you get 1.21 there. If the constraint is landing ground run, then you have to use the following equation, which is a little more complex. But anyway, given SR here, you can take TW on the other side, and then you'll be able to plot it. If rate of climb is given, okay, all these equations you'll need when you look at the case study, because the case studies will have this kind of requirements. If rate of climb is given, then you have whatever given rate of climb as the numerator divided by CD naught K W by S plus 1 over L by D max. Okay, now here initially you start with L by D, whatever max L by D you think you have, and that's because you have to guess at the CD naught and K, and then you can plot this in terms of W by S. If maximum speed is given or maximum Mach number is given, then again you can you know that thrust to weight ratio is a function of velocity, maximum velocity, and this term involves CD naught term, and this is the KCL square term. That's why you have V square at the bottom and denominator, and you have V square at the numerator. So if V max is given, this equation you use for plotting W by S by T by W. So here is a more detailed figure where it includes climb requirements at sea level and climb requirement at a higher altitude, climb landing run plus minus distances, all that. So in this case, the wing loading is mass loading, actually kg per meter square. It doesn't really matter because it's only a factor of n in this. Left hand side is not dimensional, so it doesn't matter. Okay, and what you have is different plots and some data for actual aircraft plotted here also. So for example, a MiG-80 is one of the aircraft which India had acquired. Similarly, BAE Hawk is here, and some other aircraft are also there. So this shows you that this is how people decide on what is the wing loading and what's the thrust loading required. Okay, and I have made an Excel sheet in which you can go and change the mass of the aircraft and wing area and all kinds of things, and then see how it varies. Uh, it's not enough if you come with one constraint diagram like this. You also need to do what's called a sensitivity analysis, which means that you have to see, suppose my stall speed can be relaxed by 5% or 10%. Suppose I have a slightly better CL max than I anticipated. How is this curve going to change? So this kind of what you do is a sensitivity study, and you can vary this here and there, and then say, okay, fine, I will choose this. That way you are assured that even if the CD naught, whatever you assumed, is increased by a little, you are not going to be affected because you already computed and seen that. So this is another plot which is done. This is called a carpet plot. So carpet plots used to be very popular in earlier days when we were doing everything by hand. So with calculation, you come out with a graph like this. So what you see on the left is the stalling speed, and on the y-axis, and what you have on the x-axis is the cruising speed. Okay, so in this case, the desired cruising speed is 180 kts, and the desired stall speed is 59 kts. So these are the levels you want to look at. Okay, so now what I do is I assume a wing area, and then I assumed a CL max. Okay, so if I assume a wing area of 180 feet square and a CL max available as 1.7, this will be my stall speed. And if I am willing to take a slightly higher CL max, this will be my stall speed. So what I do is I take a wing area, and for that wing area, vary the cruise CL maxes and get all these points 1, 2, 3, 4, 5, 6 like that. Okay, the next, what happens if I compute, if I reduce my wing area from 180 to 170 feet squared. So if the area of the wing is less, you obviously have to fly faster for the same kind of load, because lift is half rho square into S. S goes down, V has to increase. So for same 170 feet square wing, I do this 1.7, 1.8 CL max. So if you see here, I have all these curves here, and then I join them. The advantage of this is, let's say any point here which is too high, and then you want to know what it be somewhere in between, then I can say 140, 130. Let's say I'm looking at 135 feet square, which is not there in this. So I'll take somewhere in the midpoint, and instead of 1.7 or 1.8, I got 1.75 as the CL max. The value of the cruise speed and the stalls would be somewhere like this. So you can actually use this carpet plots to arrive at interpolations in between. Now, of course, you can use fancy programs to arrive at that multiple times. But earlier days, when we were doing this with a handheld calculator or a slide rule, we would derive at this carpet plot, and then you're free to vary the wing area from 180 to 120 and the CL from 1.7 to 1.7 to 2.3, and then get the cruise speed and the stalling speed combination by using this graph and plotting in that. So this graph is being done with certain conditions. CD minimum is 0.25, aspect ratio is 10, which means it's a passenger aircraft, and the empty weight is 3,400 pounds. So this is the initial condition for which you have made a carpet plot. Okay, so before you proceed with the design, the first step is weight estimation. The next step is looking at the constraint diagram. Okay, so one way to derive the constraint diagrams is to look at the requirements which are specified for different type of aircraft. So now let's do a quick recap on what different types of aircraft normally specify. Let's start with the passenger aircraft. Passenger aircrafts like Airbus 380 or Boeing 777 or something like that. So what do they specify normally? They would say number of passengers, what they would like to carry, maximum number of passengers. And they would also say, what should it be, range? That could be short or medium or long range. For example, they may say 50 passengers with only 600 kilometers range, or it could be 300 passengers, 7,000 kilometer range, or it could be 5 passengers, 7,000 kilometer range, in which case it would be a business jet, where somebody like Ambani or Adani can go from here to Frankfurt on their own plane with only 4 or 5 people. So it could be number of passengers, the range. So the number of passengers means that it will give you an idea of the payload weight. That payload weight of the passengers, also number of crew members and all that. Range will give you how much fuel you have to carry. And is it wide bodied or conventional? That's something which they can specify. Wide bodies, most of the new Airbuses are wide bodied. The older aircraft were conventional narrow bodied aircraft. Here, the design drivers, what really matters to a civil passenger aircraft operator or manufacturer is the operating cost, dollars per passenger per kilometer. Okay, and this is of course influenced by the fuel cost. Hence, a choice of high bypass turbofans is absolutely essential. There you have no choice. Unless you go for high bypass turbofans, you will not be able to meet the operating cost. So the moment you say passenger aircraft, turbofans, high bypass turbofans automatically pick themselves. Okay, so that is there, and of course you'll have to look at emissions. Nowadays, emissions and acoustics are becoming a serious issue in terms of environmental pollution. So they are looking at how do we reduce the noise. Noise could be from the engine. With the bypass engines, the engine noise is anyway lowered. The other noise could be if you're flying at supersonic condition, then there are shock waves. Okay, so that is one thing. The other things are chemical pollution issues. They kind of when you burn hydrocarbon fuel, even if 100% efficient combustion, you will still get carbon dioxide and water. That's the two final products of a hydrocarbon burning. Of course, the combustion is never 100% efficient, so you'll end up with carbon monoxides and things like that. You will not get nitric NOx emissions because most of the engine are burned at a lower temperature just to prevent the turbines from being destroyed. So they have a less chance of that, but you're dumping carbon monoxide and carbon dioxide at a very high altitude where you are flying. So the pollution from aircraft is a significant thing which now most of the aircraft manufacturers are looking to control. And most of these passenger planes generally fly at 12 to 11 to 14 kilometers altitude at around 0.84 or less than that, 0.85 Mach number. The idea is to fly as fast as possible, but still slightly less Mach number so that you don't have any shocks anywhere on the wing, which can of course increase your CD0, which you don't want to do. Flying at this altitude, 12 to 14 kilometers altitude, is because it's a nice trade-off between reducing density and reducing thrust availability. So thrust availability goes down by a factor alpha, as I said, but the density and other things, the drag is much more dramatic. So at this altitude, around this, depends on each aircraft, could be somewhere 11, 11.5 or 12.5 like that. But ballpark number around this altitude, you have the best possible flight condition, meaning that minimum drag and most efficient if you fly at 0.85 or slightly less than 0.85 with no shock waves and none of those things. So passenger aircrafts, the requirements will come like this. So now let's look at some design charts from Professor Kundu's book. If you look at small capacity passenger aircraft, that meaning 15, 20 people kind of thing. On the x-axis, you see maximum takeoff mass in terms of kgs, and on the y-axis, you see the number of passengers. Okay, so let's say you're looking at 100 passengers, aircraft 100 passengers. Your most likely maximum takeoff mass, if you look at this curve, will be around 50,000 kg. So that's the ballpark kind of thing. So if you have 200 passengers in mind, you are likely to be around 100,000 kg. Now there slight difference happens depending on the range. If you're around 2000 nautical mile range, then for 200 passengers, you will be around 100,000. If you are looking at 1,500 nautical range, then for 200 you will have a slightly lesser weight here. So the range factor kind of differentiate this curve with that. But if you're at a lower number, let's say about 100 people, 100 number of people, passengers, then really all the three curves, whatever is the range, they fall around the same point. So quickly, the moment I say my aircraft has to carry 100 people, you know that you are going to be somewhere near 50,000 kg mass, not weight. So similarly, if you have a higher capacity, like 380, the number of people is 200, 300, 400, 500 people, then the range also becomes a very significant point. Okay, so if you're looking at 500 passengers, there are not many aircraft of that size, and around the range of 3,500 nautical miles, then your weight is likely to be about 300,000, maybe 3,200, something like that. And if you're looking at a larger 8,000 kilometer range, then your weight is going to be different. At 500 people, 8,000 you will hit 500,000 thing. Of course, if you have got 500 people, they are hardly likely to be traveling only 2,000, 3,000 nautical miles. It's likely to be a longer flight. But anyway, these are the figures, the curves drawn based on existing aircrafts. All these points are existing aircraft, and they are not named, of course, for the reasons for confidentiality, but rest assured, these are all existing aircraft. So you're not likely to be very much different from this if you are designing this kind of thing. Okay, so there are a little bit of confusion in the way people define manufacturer's empty mass. This is the finished aircraft mass rolls out from the factory line, MEM. So that has nothing else. It's only the aircraft, it rolls out. OEM, it's not original equipment manufacturer. In this case, operator's empty mass is MEM, the aircraft mass, plus crew, plus consumables. Okay, it is now ready for operation. So consumables meaning fuel and lubricants and everything else, plus the crew and everything. Okay, so maximum takeoff mass is OEM plus payload, and now you have fuel. When you say consumable, there's a minimum amount of fuel needed, and that is there. Now, if you're looking at changing the amount of fuel, for example, you never really fill the aircraft with full fuel unless required, because that would be a foolhardy since it has to carry that fuel. So maximum takeoff mass is OEM plus payload, number of passengers or bombs or whatever, and the full fuel loaded to the maximum design mass, complete thing. Okay, so this is usual definition. So now let's look at a table. The range is given in terms of nautical miles. That's a standard aircraft terminology, varying from 1,500 nautical miles, 3,500, 6,500, 800. So maximum takeoff mass per passenger, meaning kg per passenger, maximum takeoff mass. So if it is only 1,500 nautical miles, you have 400 kgs per passenger. So if you have 10 passengers, it will be 4,000 maximum takeoff. If you have 100 passengers, it's 400 into 100. So that this is the multiplying factor. So now let's say you are looking at a mission profile with 300 passengers. Okay, that is not there in this. You have to arrive at that thing. And a 5,000 nautical mile range. So 5,000 is not here. You have to interpolate between 3,500 and 6,500. Okay, and the estimated takeoff mass is 750, because 3,500 to 6,500, if you interpolate for 5,000, you will get around 750. That's somewhere in between 600 and 900. Into 300 will give you 225,000 kg mass. And strangely, this is also comparable to the Airbus 300-300 that has the same kind of number of passengers and range. So the point in this example is that while this may look ridiculously simple, the numbers you get will not be atrocious. They will be well within the errors of what you expect. So it makes sense to go ahead and use this initially to estimate the weight. You'll of course be using different techniques for a weight estimation, and as and when you choose some component, let's say you've chosen your engine and you know that engine's weight, that adds to your accuracy. And you also have the fuel weight that also will improve your accuracy. So as you progress in the design, your weight estimation will become more and more accurate. Initially, you start with rough estimates like what we have seen here. So this is a curve data. Not a curve, we could not fit a curve in this. This is a data of from again Matt English book for cargo and passenger aircraft. So what he has done is he has taken empty weight to takeoff weight ratio and plotted it against the takeoff weight. So you can see here all kinds of aircraft, A310, Airbus 300, Airbus 330, and Concorde and A380 is right here at the tip, because 380 was designed for extended flights. Incidentally, they've stopped making this 380 anymore. No more 380s will be made. There are, of course, plenty flying around in the world. So similarly, for fighter aircraft, data for fighter aircraft, for example, in this case, you have F-16 and F-15, these different kinds of fighter aircraft. Okay, so if you look at empty weight to takeoff weight, then what will be the total takeoff weight in terms of 1,000 pounds? Okay, you can also find out what is the takeoff weight of Tejas, and then plug it in here and see how it looks in terms of WE by T naught. I suggest you do that. Tejas takeoff weight is the takeoff mass is 10,000 kgs, so you can try and see where it fits in. So there are some linear correlations which have been given by Mattingly, because this is an engine design book. Mattingly and Raymer and Roskam have all this data. So gamma is equal to 1.26 W takeoff by. So these are the correlations which are given there. And if you look at OEM, the operator's empty mass versus maximum takeoff mass for all aircraft, all types of aircraft, you will see here the best ratio, empty mass ratio you get is around 50%. You're not going to do better than that. In fact, as the takeoff mass becomes smaller and smaller, structural mass becomes less efficient, so that will be slightly higher percentage. Larger the structure, more efficient you can make it. Smaller structure, there is not much you can do, so there will be a large difference in that. So you see here, the empty mass goes down asymptotically and it hits the minimum around 0.5. So unless you come with radically different types of materials and enormously different types of structural design, you're not going to be better than 50%. Okay, so this is for all aircraft. And of course, mid-range Boeing and Airbus families also you can look at, but no, as I said, no, they're all somewhere slightly better than that, more than that, and things. So all these charts anyway, I'm going to share with you, so you don't have to worry about that. And the fuel load. So this is the fuel mass in terms of kg and the maximum takeoff mass. So again, this depends on the type of aircraft you are having. Okay, so there again, the range and all that, so you can't directly correlate it, but depending on the range, it depends. Same aircraft, if it is has to fly at a longer range, then it has more fuel, but in shorter ranges, it may not fill the fuel fully. So this is something, but you can look at the percentages. The highest percentage of fuel load is 60%. Okay, but most of the times it's around 10-15% somewhere here, depending on the things. So again, wing area versus takeoff mass. Okay, so takeoff mass for small aircraft, 10,000 kg range. Tejas is around 10,000 kg range. 10, of course, now is about 11 to 12. So if you look at this point here, you are looking at a wing area of around 30 meters square, whereas for Tejas it's around 38. Because the weight is slightly more than 10,000, you have somewhere around 38, and this figure is pretty, quite interesting. And you can see that the other fighter aircraft also have a similar wing loading. And wing loading, you are looking in terms, of course, mass loading in this case. For aircraft like Tejas, you are looking at about 2,800 newtons per meter square or 280 kg per meter square. So similarly for single aisle aircraft, single aisle meaning passenger aircraft with only one, 3 seats on one side, 2 on one side, and there's only one aisle in between. So it's a very small, narrow body aircraft. And for them also you have wing areas and limitations, all that. So, okay, that is the civil aircrafts. Now, if you're looking at military aircraft, what are the kind of requirements we are looking at? Military aircraft requirements are usually very, very key, and they are signatures in terms of radar cross section, in fact, of infrared and acoustic signature, range and endurance, rate of climb, time to altitude, turn rates, maximum and sustained turn rates. So for military aircraft, performance is the design driver. Okay, you have to meet the performance. Nobody is interested in saying that if you reduce the rate of climb, I'll give you better fuel consumption. No, that's not acceptable. So here, performance is the design drivers. Design drivers are dependent on end use. What is the use for which it is done? So maximum payload and range for bombers, payload and acceleration for fighter bombers, turn rates, rate of climb for air superiority aircraft. So if you are looking at a B-52 or the B-2 bomber, there the payload and the range is the most critical thing. They are not going to do any fancy turn maneuvers. If you are looking at fighter bombers like the Sukhais, which can carry bombs as well as do certain amount of air combat, then payload and acceleration are important. But if you're looking at Tejas kind of aircraft, it is only air superiority. It cannot carry much bombs. It's a light aircraft. Then you're looking at turn rates, rate of climb, and those kind of things. So basically, what drives the design depends on the end use of the aircraft you're looking at. Unlike the passenger aircraft, which had a preferred altitude and Mach number, military aircraft don't have such thing, unless of course it's a long-range troop carrier. Then if it can fly at a very as the same altitude as 11 and 0.85 Mach number, because these peacetime troop carriers are not in combat, so they can fly at that. Otherwise, they are driven by mission. So whatever is the mission requirement, altitude and Mach number, the aircraft has to do. So here is another plot, which is takeoff thrust to maximum takeoff weight. So this is the T by W ratio. Okay, now T by W is a factor depending on the type of aircraft. So as I said, most of the passenger aircrafts, long-range passenger aircrafts, T by W is lower, and for fighter airplanes, T by W is larger because you want to have better acceleration. So if you look at military aircraft statistics by Kundu's book, maximum takeoff mass in terms of kgs, and operational empty mass is one side, and then of course the portion of that, what will be the operational empty mass is this. So here some for around 12,000 kgs Tejas, you have an operational empty mass close to 5,000 kgs, roughly 50%. That's something which you cannot get away with. Similar for different kinds of heavier aircraft. This is for the internal fuel load. This is for the payload, payload versus maximum takeoff weight. So if you're told your military aircraft has to carry 10,000, no, not 10,000, it's too small, 30,000 kgs of bombs, then you can look at what will be the payload 30,000 kgs, and if not in this figure, the next one, and then find out what will be the weight of the aircraft based on this curve. And again, takeoff weight and wing area per square meters, different aircrafts, wing loading and types of aircraft. So you are looking at, for example, Tejas kind of thing should be somewhere close to here. But if you have a slightly more agile aircraft, then you will have a lesser wing loading. Remember, if I reduce the wing loading, my aircraft becomes more agile. Similarly, maximum total thrust, takeoff thrust, and all that pictures. So some useful relations in case you end up with a case study which has a propeller-based aircraft. Then for maximum range, CD is equal to 2 CD naught, and for maximum endurance, CD is equal to 4 CD naught. Okay, and the CL for maximum range is under the square root CD naught by K. K being 1 over pi s peak, I have taken it up honestly. And for maximum endurance, CL is 3 CD naught, 3 CD naught by K. So basically, these are the numbers which are there. In case you want to do a propeller design, you will have to look at that. Similarly, for jet aircraft, maximum range is when CD is equal to 4/3 of CD naught. Maximum endurance is when CD is equal to CD naught. So this kind of equations you should have as a small reference card when you're designing, because every time you can of course derive all this from this equation, CD is equal to CD naught plus KCL square, where it's better to have this in one place, ready reckoner. Whenever you're doing it, you can use this terms. For example, if you want the maximum range for a jet aircraft, this is the velocity at which you have to fly, 1.316 times under the square root and all that kind of thing. So summarizing, what we are looking at is the statistical data, key importance of statistical data, and how we can use various correlations and thumb rules to get started on the design. Okay, I want to emphasize here, to get started on the design. This is not going to be there after the second or third iteration. Things will start changing. As your design progresses and you become more and more confident of the kind of engine you're going to use, the amount of fuel you're going to use, the type of wing material, the type of landing gear, your weight estimation will become more and more accurate, your wing loading calculation will become more and more accurate, and your performance will become more and more realistic. So various component weights of the aircraft are also part of the statistics, where you can, for example, look at Airbus or Boeing and then see what is the total weight and the wing weight percentage, and that is something which will also give you an idea. The importance of preliminary weight estimation cannot be overemphasized, and of course you also have to look at its assumptions you have made on that and sensitivity end results. Most of the statistical data available are for older generation aircraft, means their materials will be slightly behind what we have now in terms of specific strength, in terms of, let's say, temperature resistance if you are going to use an engine, and you may use more composites than they have used earlier. So you always have to keep the assumptions in mind and then do a sensitivity studies and vary all the parameters you have chosen, 5% this side, that side, and see what happens to the end results. If you're still within the requirements of whatever design, then you are safe. Okay, so I'll stop here now, but I'm not stopping the lecture. I'll switch to another presentation, which is the 5 case studies. I'm going to give it to you guys. As I requested, you have to formulate teams, 5 teams, and each team will have one of these case study. Okay, and I'll assign the case study, and then that you can work on that. So then we'll try and use all these graphs and design charts, whatever, and the processes on that specific aircraft, so that we are no longer talking in air. We are, what the Americans know, we are going to hit the rubber on the road. Okay, just to hold on. Let me. Okay. So what I'm going to do here is another PPT, which I just prepared some time back. These are requirements case studies, which you are going to work with your individual group. The first case study is a military trainer. This is an actual design requirement which had come to our notice when we were discussing with some companies related to HAL. So this is a military trainer where the takeoff mass is less than 2,800 kg, which is capable of a load factor of +6 and -3, ceiling greater than 6 kilometers, endurance greater than 3 hours, rate of climb 10,000 feet per minute, roughly more than 50 meters per second, and a glide angle around 10 degrees. It should be not greater than 10 degrees. Okay, so you're looking at a glide angle maximum 10 degrees. So from this, what all can you guess? The glide angle less than 10 degrees will tell you what should be the L/D ratio you're looking at. Endurance 3 hours will tell you how much fuel you're going to carry. Ceiling 6 kilometers will tell you something. Load factor plus 6 will tell you something. And rate of climb 50 meters per second will tell you something. So from these requirements, you should start deriving different components of the design. Okay, so that was the first one. The second one is more mundane. This is design an aircraft that will carry 80 business class passengers and their associated baggage over a design range of 7,000 nautical miles at a cruise speed equal to or better than existing competitive services. Meaning this means that you are looking at 0.84 and 12 kilometers altitude or better if possible. What happens if you increase the Mach number from 0.84 to 86 is that you will hit the transonic condition and you may end up with some other case. So either you redesign the wing, a better wing than what is there in Airbus, or you stick to whatever is existing. And then of course there are some non-specific requirements like provide customers with equivalent or preferably better comfort. Okay, which really doesn't mean much. But these are the requirements which normally come from the operators. And then, but this is crucial to operate from regional airports. Regional airports meaning Coimbatore, Madurai, Hubli, and these kind of things, where the runway length is likely to be shorter than international runways. Okay, and you are also expected to investigate alternative roles for the aircraft. Meaning, can this be from business class jet? Can you use it for some other purpose? So do a brainstorming and see what can be done. Okay, so 80 business class passengers, either that or 7,000 miles. What else can you do with this aircraft? So that's these two. The last two are crucial inputs. The first two are crucial inputs. This one about comfort and all is just fluff. Really doesn't matter. And then the third one is an advanced military trainer. So the first one was a basic trainer. This is an advanced military trainer, and you have ISA plus 20 degrees centigrade to 11 kilometers. And what this means is when I say sea level density is 1.225, sea level temperature is something, that is ISA. Now you are asked to measure the performances ISA plus 20 degrees centigrade up to 11 kilometers. Okay, then also it has to operate in ISA minus 20 degrees centigrade up to 1.5 kilometers altitude. So this one minus 20 means it implies that it is somewhere near the Himalayas. It's closer to Sichuan and Leh kind of thing, where the temperature is much lower than international standard atmosphere. ISA plus 20 means you're looking at an airbase in Gwalior or some such place, which is pretty hot, Chennai, for example. And then you're looking at maximum operating speed. V suffix MO is 450 knots at sea level clean. Clean meaning there are no external stores, missiles and bombs and stuff. Okay, maximum velocity 180 knots at sea level, undercarriages and flaps down. So that means your undercarriage and flaps, when they are down, you have to compute the drag, different drag than what you had here. And then undercarriage and flaps down, meaning that basically you're nearing landing or touchdown case. Turn rate, sustained turn rate is 4 degrees per second, which is pretty. Sorry, not the maximum sustained G at sea level is 4. Okay, and maximum sustained G at flight at 250, that's 250,000, 25,000 feet is 2. Turn rate is 14 degrees per second, which is reasonably high because it's a military trainer. Most of the combat airplanes are around 16 to 17. So this is around close to 14. So the pilots can be trained at that maximum. Instantaneous turn rate, 18 degrees per second. Instantaneous turn rate means, of course, the altitude is reducing, meaning at this turn rates, the load factors are such that and the drag is such that your thrust is not able to keep up. So you start losing altitude. So this is case study 3. It also has certain other specifications. Approach speed, field approach speed is 100 knots. Takeoff and landing ground runs in terms of distance is 610 meters. Crosswind capability 25 knots desirable. Climb service ceiling 12.2 kilometers. Climb 7 minutes SL2, FL250. Node 1 flight level is 100 feet. So that's 250 means 25,000 feet. Okay, so 7 minutes to climb from sea level to that. Descent 5 minutes from this to FL20. Basically, maximum 15 degrees nose down descent. Ferry range, 1000 nautical miles. Ferry range means it's not returning to the starting point. The aircraft goes from point A to point B. Radius of action means it goes to point B and comes back. So that will be, of course, less than this. And it should also be able to carry external tanks and go to 2000 nautical miles. This is the case 3. It also has structural, this is a more detailed specification than the first two. You have +7 as the maximum thing. Maximum design speed is 0.8 Mach number. There are also hard points in terms of on the structure where you can hang stuff, 500 kgs stores. And so these ones, number of stores and all you need to find out the weight of the aircraft. Okay, because you are carrying those. These are all payload. And of course, there are other things like provision for air-to-air refueling and all. These are more detailed, which won't affect your initial design. So case 4 is advanced combat aircraft, and in this case, you are looking at 30,000 plus minus 1000 kg class. This is much heavier than anything which at present Indian Air Force has. And you're looking at a maximum speed of 2.25 Mach number at 12 kilometers altitude. Super cruise at Mach 1.8 at 9 kilometers. Super cruise means it is reaching 1.8 Mach number without the use of afterburner. Right, so this is a very, very important. That means the engine thrust, dry thrust itself should be able to reach with that. It should be able to reach 1.8 Mach number at 9 kilometers altitude. So range should be more than 2,900 kilometers. Service ceiling is 19 kilometers. Rate of climb at least 200 meters per second. So if it's higher, the better. Maximum design loads -3 and +9. This is the advanced combat aircraft case study. The next one is advanced military transport. So this is a next generation strategic airlift military transport plane with the following details. Unfueled range is 11,500 kilometers with a baseline planned load of 55,000 kg mass. So this is a massive guy. So maximum payload weight shall be no less than 135,000 kg. Cruise Mach number no less than 0.6. Time to top of climb and climb to initial cruise altitude no less than 20 minutes. It should be around 20 minutes with 90,000 kg. And takeoff field length is maximum payload and landing not greater than 2,700 meters. Okay. So when you say landing length should not be more than 2,700 meters, and from that you can derive what is the touchdown speed and what's the stall speed, and I'll talk about that in the next class. So I'm going to leave this case studies, and I expect all of you to form 5 groups and tell me which one is going to work on what. All the case studies will be chosen. I'm not going to allow 2 teams to work on the same case study because that doesn't make sense. Right? You should be able to have different varieties. At the end of the class, we can sit and discuss. All groups will discuss their presentation, so everybody gets a feeling of how you look at a military transport design, or how you look at a combat airplane design, or how you look at a trainer design. Okay, so at this point,